The next speaker in this session is Zach. He is going to talk about optimizing electric motor controls to improve efficiency. So Zach received a Bachelor of Science degree in Electrical and Electronic Engineering from Bangladesh University of Engineering and Technology in 2009. From 2009 to 2014, he worked for Robi Exita Limited in Bangladesh. He received his PhD degree in electrical engineering in 2019 from University of Akron. During his PhD studies, he worked as a research assistant at the Advanced Energy Conversion Lab of University of Akron. In 2019, he worked for LG Electronics as part of the motor design R&D team for a brief period. Since October 2019, he has been working as a design and control engineer for Tula Technology. His responsibility includes the design of electric machines for advanced control applications and facilitate motor control programs. He's an IEEE senior member and well connected to the community. And welcome, Zach, to our user conference.
Hey, hello everyone. Yeah, thanks, Sinan, for introducing. Let me. Yeah. Okay. Sinan, I'm not able to share my screen. Looks like it's disabled.
Yeah, sure. I will ask Brian.
I can, yeah, Zachary, let me look at that 1 second, okay? I'm going to do that right now, so you should get a message.
Yeah. So I hope you see my screen.
Mm-hmm.
So
yes, we can. Thank you.
Yeah. Hello everyone. Again, I'm Jakil Islam, and I work on electric motor design at Tula Technology. So, and I'm presenting from San Jose, California. Today, I'm going to talk about our dynamic motor drive technology, which is an interesting approach for optimizing electric motor controls to improve the efficiency. So, at first, let me introduce my company. So, Tula Technology, as a Silicon Valley startup, was founded in 2008, and we're located at in San Jose, California, and we have a facility in Michigan too. Since the beginning, Tula Technology has focused on improving the fuel efficiency of IC engine vehicles. Our patented technology, dynamic skip fire, which is an individual cylinder activation deactivation control technique. DSF improves fuel economy and reduces NVS level and reduces the gas emission like CO2 NOx by skipping some cylinder activation. And this DSF technology has been a big success for the company, already implemented in over 1 million vehicles hitting the road, and it is well appreciated across the automotive industry. However, today I'm going to talk about our latest innovation, dynamic motor drive, which is for electric motor drive application. Basically, the dynamic motor drive and dynamic skip fire both have similar philosophy of controlling the machines. So both IC engine and electric motor has some sweet spot, means peak efficiency region, and Tula's DMD control finds a way to operate the emissions at their peak efficiency for a greater percentage of time. And DMD can be useful in electric vehicle as well as in HVAC application, windmill application, and so on, wherever electric motor drives are used and efficiency is a concern. So let's take a look at the concept behind the dynamic motor drive. And at first, let's start with the system efficiency mapping plot of a typical electric motor drive. And you see the system efficiency map has high efficiency zone, and around that, it has low efficiency zone. And this line is the highest efficiency torque line, and it signifies that any point in this line experience the highest efficiency possible for that particular speed. And in applications like electric vehicle, you will see there are lots of operating point in this low efficiency low torque zone. So the objective of DMD is to help improving efficiency for those operating points in this region below this highest efficiency torque line. So let's see how DMD will do that. So in DMD operating mode, in response to a particular torque request like that, the motor will be intermittently operating at highest efficiency torque. So in other words, for a particular torque request like that, the motor will be operating either at highest efficiency torque for some time, then it will be quickly transitioning to zero torque, operate there for some time, and then will be transitioning to again the highest efficiency torque, and this cycle will be repeated. And if you see the torque versus time plot, the motor is transitioning between zero to highest efficiency torque and going back to zero torque. So there are a couple of points to be mentioned. The transition loss has to be very small. The loss at the zero torque point should be small or negligible. The noise and vibration has to be within acceptable level. And so the duty cycle, this is dependent on the requested torque. So the time average for a particular cycle of the pulse torque should be equal to the requested torque. And another point to be mentioned is DMD gain is only possible below this high efficiency torque line. And theoretically, DMD can achieve efficiency of this line to any point below that in an ideal scenario. And DMD cannot help for points in this region where the efficiency is still low, but it's above the highest efficiency torque line. So let's expand on this concept by contrasting. So in the right side graph, you see the time history of efficiency in conventional operation. Here the torque is varying over a fixed speed, and you see the motor is achieving low efficiency when the torque is lower. And again, it's reaching higher efficiencies at higher torque, means operating around the sweet spot. And in contrast, for dynamic motor drive operation, the motor operates intermittently, but only at higher efficiencies. When the torque request is low, the torque and current excitation is pulsed for optimal efficiency. When the torque request is high, the motor operates continuously or conventionally. So if you compare these two time history of efficiency, so in conventional operation mode, the motor will experience lower efficiency for some lower torque points, but in DMD mode, with pulse torque strategy, motor maintain higher efficiencies for even those low torque demands. So what is the control strategy? The control strategy used during periods of high torque and low torque is conceptually the same as conventional method, with conventional feedback of phase voltage, phase current, and position. And the inverter operates conventionally, and the torque modulation block contains the algorithm required to determine the frequency of modulation, pulse density strategy, and determination of torque level. So of course, noise, vibration, and DMD gain aspects have to be recorded in this DMD algorithm. So there must be certain scenario when you have to sacrifice the maximum DMD gain just because the input level is not acceptable, or vice versa. So such scenario will be predetermined and incorporated in the DMD algorithm. So let's look at the vehicle sensitivity and human perception aspect for DMD. So of course, DMD algorithm have to be optimized such that the torque modulation phenomena remains completely imperceivable by the users. The regimes of operation are determined in a manner similar to that used for production Chevrolet Silverados. A large advantage of DMD operation over DSF is that DMD can be pulsed at frequency and torque that are not coupled to the vehicle speed. So we can avoid the regions of human perception. Typical human perception is shown on the left. So it's around 0.5 hertz to around 20 hertz. And in general, this frequency range must be avoided. In addition, regions where the vehicle transmissibility or resonance is or the resonance is high also be avoided. Frequency response function of the seat track and the steering wheel are shown on the left, and the areas in which the both seat track and steering wheel transmission are low are highlighted in green. The human perception region is shown by the red block. So still we see there is a large area for DMD operation between 30 to 45 hertz, and again between 120 to 180 hertz, where perception of vibration will be very small. However, to be mentioned, these are for vehicles with DMD. And as I mentioned, DMD can be applied for other applications where there might be no human being around for most of the time, and these limitations might not even exist in those applications. So DMD can be easily applied even for those. So let's go through further details on the motor losses and see how we're reducing part of the losses with DMD. So this right side plots are very popular. These are showing the loss breakdown of electric motor drives. The top one is for motoring and the lower one is for generating operation. And if you see in both picture, the losses are inverter loss, core loss, copper loss, stray loss, and mechanical losses. And on the right side, we see the percentage of loss component with respect to the input power. And this is for varying load. And this plot is for fixed operating speed. So we see from total loss line at a certain load, the total loss portion of the input power will be minimum. So means that is the highest efficiency torque point. So if we remember from DMD, the motor will be operating at this maximum efficiency torque or at zero torque, and it will be transitioning between these two points at a certain frequency we call torque modulation frequency. So if the zero torque operation and the transition loss is lossless, the motor will achieve the efficiency for this point with DMD operation. So let's take a deeper look at equations for motor torque and losses. So this is the torque equation for PMSM type motor, which has a PM torque portion, and it also has a reluctance torque part. And we also see the copper loss, iron loss, inverter loss components. All these losses are directly or indirectly related to the current and are either linear or quadratic function of that. And the corresponding terms are circled in these equations. So this is to signify that the loss, which is linear function of current rather than quadratic, determines the suitability of motor's DMD operation. So again, the same torque equation. This equation can be applicable for interior permanent magnet motor, surface mounted permanent magnet motor, synchronous reluctance motor type, or so on. So if we look at the synchronous reluctance motor first, so for this synchronous reluctance motor, only this portion will remain. The PM torque portion will be vanished. So we can say that for synchronous reluctance motor, torque is proportional to the square of current. And because of that, to get a 2 times of torque, we only need 1.5 times of current. And because of that, from the previous equations we see for different loss components, there are some loss components which are proportional to the square of current. So those loss components will be remaining unchanged for synchronous reluctance motor with 50% duty cycle DMD operation. And there are some losses which are proportional to the current. Those losses for synchronous reluctance motor will be reduced. And for SPM type motor, we see the torque is proportional to the current, and some losses increases and some losses remain unchanged. So this is not suitable for DMD application. However, for interior permanent magnet type motor, we see the torque is proportional to the current, or also another part is proportional to square of current. So because of that, we see some losses either will increase or remain the same, and some losses will either decrease or remain the same. And this is again showing for IPM and CNRM type motor, which losses are decreasing or increasing or remaining unchanged. So let's take a look at a couple of the motor topologies from DMD loss reduction perspective. And in the continuous spectrum of motors that use either or both of reluctance and magnetic torque, whether described as a synchronous reluctance motor, EM-assisted synchronous reluctance type motor, interior permanent magnet type motor, or surface mount permanent magnet type motor, all the motors will be able to see gains from dynamic motor drive operation. However, in practice, motors that use a larger proportion of reluctance torque, like synchronous reluctance motor or PM-assisted synchronous reluctance motor, will benefit more from the intermittent operation or DMD, rather than the motors which are heavily dependent on permanent magnet. They are less they have less tendency to get DMD gain. However, good news for the DMD is that it is suitable for synchronous reluctance motor and PM-assisted synchronous reluctance motor, which does not use or use less amount of rare earth magnet, and therefore suitable for EV industry, which is desperately looking for alternate solution to rare earth PM-based motors. So let's look at the DMD implementation and what are the steps that we followed for DMD implementation. The first step is the first step for proof of concept is design and analysis step, where we evaluated the motor losses with DMD operation. So to do that, we have used EPA tool JMAC Designer brought to us by the PowerSys, and we have developed the motor models, optimize the motor parameters for high efficiency and lower torque pulsation and so on. And we also have evaluated the motors for overall losses with and without DMD for a particular set of operating points on the JMAC, based on the JMAC results. So based on that, we have selected the final design, made the prototype, and followed by the final step, which is Tula's DMD control implementation. So during the modeling and loss analysis, we worked very closely with JMAC team, and kudos to the JMAC team for their relentless support to overcome all the challenges in performing the loss analysis, especially for the special motors we use, because of the nature of this research is novel. We're frequently faced with new and unique challenges. JMAC team has always been there to resolve the issues immediately and bring a long-term solution in the next release of their software. So we're really happy to see the evolution of efficiency map tool, especially in the last few releases, that really helping us to do our DMD analysis and figure out the best motor for DMD control perspective. So again, as a proof of concept, Tula has developed a synchronous reluctance motor that uses a commercially available stator. We have used JMAC Designer to get the optimal synchronous reluctance motor design. We use multi-objective generative algorithm programmed in the JMAC Designer, and over 2000 designs were evaluated in finite element analysis process before determining the optimal design. The optimization process is almost mostly done following conventional design approaches and objectives, except a couple of additional iterations that were done to figure out the best synchronous reluctance motor design in terms of maximum system efficiency, as well as in terms of DMD gain. So our first proof of concept is an 8 kilowatt synchronous reluctance motor, which has been evaluated and extrapolated to use in a 150 kilowatt traction motor application. So again, you see this scattered plot These are obtained from JMAC Designer. This shows the average torque ripple and percentage of total harmonic distortion of the induced voltage of the synchronous reluctance motor. So use this information along with some others to select nearly a dozen of models initially, which were then evaluated for manufacturing tolerance before finally selecting one model for prototyping. And thanks to pretty good calculation accuracy of JMAC tool, and we finally found out that optimal model behaves almost similarly that we calculated from the JMAC tool. And we'll see that in the next two slides. So yeah, these are the contour plots that compare the flux linkages compared in FEA with and it also compared with corresponding to test results. So the leftmost figure is the FEA result of B-axis flux linkage, and if you compare it with the test data, you see the results are almost same, and you see the percentage of error is pretty small except some limited region at low current conditions, which can be acceptable considering the manufacturing tolerances. And for similar results are seen for the Q-axis flux linkage. So if you see the FEA and test results, they're almost similar, and the percentage of error is also again pretty small over most of the region except some region at low load conditions, so which are again acceptable. So here we will see the impact of those accurate prediction from FEA in the DMD concept. So we ultimately see that FEA predicted DMD gain is attainable based on the test data. And on the top plot, you see the motor efficiency map that is captured in the JMAC Designer tool for the synchronous reluctance motor. And down there, we see the motor efficiency map that is plotted based on the test data for that same synchronous reluctance motor. And if you see, these are very similar. And so we use those motor efficiency, motor loss data for getting the DMD gain map. And these plots are showing the DMD gain map for FANPAM for a HVAC application, which with 4 operating points. So this is showing the gain possible for a particular region. And you see the test result is also similar, and the DMD gain map is similar in both FE and test, which is very significant for us. And you see here, this is showing the DMD gain. The bar 4, there are supposed to be 4 bar chart, those which are indicating these 4 points, 4 load points, which are one is for 6 hour, 9 hour, 6 hour, and 3 hour, and at different percent of load. And so if you see the percentage of energy saved with DMD for this particular application, we see that around nearly 1% energy can be saved with DMD, and which means 8% loss can be reduced based on FEA. And from the lower one is showing for the test. So we see the percentage of energy can be saved nearly 1.39%, and percent of loss reduction can be possible around 11.47%. And so this little increment in the gain is understandable because there are some losses which are which are little higher in the actual test scenario, for example, like core losses, and that can be saved again by DMD. So that's why we are seeing little higher energy saving in actual DMD application. So let's see the gain that is made possible by DMD for synchronous reluctance motor. So let's see the projected loss reduction made possible with DMD for a vehicle drive cycle. So we consider WLTP drive cycle, or in full form, worldwide harmonized light duty vehicle test cycle. So this plot shows the loss reduction possible in inverter alone. The control plot in the right is showing the percentage of loss reduced in the inverter under DMD operation. So through a large section for motoring and generating operation, we see the DMD gain is possible. Even for some point, it's around like 150 Newton meter. So, and we see at low loads, losses can be even reduced further. More than 50% DMD gain is achievable in many points. So the accumulated losses for both conventional operation and DMD operation is shown in the bar chart on the right. So over the WLTP cycle, the conventionally operated inverter loss is over 0.08 kilowatt hour of energy. And in contrast, the inverter loss using the DMD strategies is less than 0.03 kilowatt hour. So similarly, we can evaluate the reduction in copper loss. However, copper loss increases dramatically with higher current and higher torque, which means the area in which the copper loss are reduced will be small, and that's what we predicted when we see the torque equation and loss equations before. So the copper loss is supposed to remain almost constant. So that's what we see. There is a very small change in the copper loss. So the core loss are reduced in a much larger area of operation, sometimes even exceeding 200 Newton meter. Although the core loss reduced substantially, in terms of vehicle losses, core loss are much smaller sources of inefficiency for this particular analysis. So that's why, although it's significant, and the total amount was small. So, but in total, we can see a large reduction in motor losses, system efficiency losses. So throughout the WLTP cycle. So in total, the powertrain losses are reduced from 0.19 kilowatt hour in the WLTP to around 0.13 kilowatt hour. So projected losses for synchronous reluctance motor are reduced by approximately 1/3 using the dynamic motor drive technique. So again, over the WLTP drive cycle, these reduction in losses translate to gain over 2.5% of dynamic motor drive, which is impressive considering the fundamental dynamic motor drive technology use only conventional hardware and only changes in the software algorithm. So this improvement in efficiency will allow synchronous reluctance motor to compete with the efficient motors that are currently made possible only with heavy use of rare earth materials. So the dynamic motor drive can help eliminating enormous cost and supply chain challenges related to the rare earth permanent magnet based motors, which offer, so in total it will be offering superior value. So in the end, I will say the proof is in driving, and Tula Technology currently retrofitting a Chevrolet Bolt with synchronous reluctance motor and DMD algorithms to demonstrate the imperceptible and efficient control of the dynamic motor drive technology. It will be available for evaluation to select OEMs and industry partners by the end of the year. And thanks for taking the time to learn about dynamic motor drive, which is to make electric vehicle fleet more efficient. So that's the end of my presentation. And let me know if you have any question regarding DMD. I will be more than happy to answer any question.
Okay. Zacharel, thank you. So I just wanted to express, my thanks to both Simon and Zacharel for the time and resources you gave to your presentations. Thanks so much, and thanks for sharing your JMAG experience with us regarding efficiency map and both presentations were very informational. Thank you. So we have a little extra time for Q&A. We're running a little bit ahead. So we've got some extra time for questions. So if participants can have some things they want to ask, you can post them on your Q&A panel. So I do have a couple of questions that have come in. So the first one I believe is for Sinan. Sinan, can we calculate efficiency map for linear machines on JMAG?
Yeah, JMAG officially does not support linear motors for speed priority efficiency map generation. It may be added in the future, but just like axial flex machines that can be used, even though it's not officially supported either, but you can generate actually. I will try that and get back to you if the linear machines with magnets can be done with the efficiency map tool. Thank you for the question.
Okay. Thanks, Sinan. So, Sinan, I do have a second question here I believe, for yourself. Which PWM mode, such as SVPWM, DPWM, is available?
Yeah, even though it's not in the question, but I assume it's this question is for accuracy priority, because the speed priority does not consider the more than the sinusoidal current source. So with this accuracy priority, you can have any type of control diagram as you want. There are Python script components, and you can make your own Python script that represent SV, PWM, DPWM, and any other types that you create customized by, PWM by yourself. So it's very flexible. It can do anything basically if you can form them into a Python script. That's a very good question. And as Dr. Yamada said, JMAG will have more control templates, which can be used for transient simulation and or accuracy efficiency map generation. So if for now you have to make the script by yourself to make your own customized block, and if there are more control templates, there may be SVPWM or DPWM in the future, then you can use the template. It will make it easier to use.
Okay, Sinan, thanks. So, Zacharil, I believe you have a question that came in for yourself. So, this one asks, the iron loss that you got from testing the prototype, how are they correlating with the loss maps that you were getting using JMAG efficiency maps?
So, yeah, it's a very nice question. And I think just pointed the most important point. So, the iron loss we got in the test, there are some differences. So it's the difference is max for that particular loss portion, and we understand that it should be kind of a little bit different or offsetting from the FEA. So, but still it's acceptable, and we found it's little more than the FEA test result we got. And you see, because of that, we get higher gain compared to the predicted by FEA.
Okay. Zacharil, thank you. Okay. See if we have another question here. Here's one for Zach. So Zach, are there any limitations on the type of system where DMD can be used? such as the inductance and inertia of the machine or inertia of the drivetrain?
So yeah, that's a very good question, I would say. So these are very important, especially for example, the inductance. So there is rapid transition involved, like the torque modulation frequency. So that is limited by the inductance. So the DMD will face like higher challenges for like the motors like induction motor, but like if the torque modulation frequency is still applicable, like acceptable for that particular applications, then we can still apply DMD. But yeah, definitely these all are kind of the will be limiting the suitability of DMD for particular applications. Yeah.
Thanks for that answer. So looking at our question panel, and I'm not seeing any additionals. So let's, please, participants, if you have any questions, feel free to pose those. We have a few minutes left that we can do some Q&A here. I do have another question coming in. So for Zach, how does that DMD impact wear and tear of the transmission itself?
So wear and tear in the transmission. So far, so I think I will leave this question to be answered later, but our mechanical team is working on that, and we so far we have seen very minimal impact, and I will welcome this question communicated to me later on to be answered by corresponding mechanical engineering team. I mainly focused on electromagnetic design aspect in this presentation. Yeah. So Brian, you are muted maybe. Brian.
Yep, thank you. We're gonna maybe just hold on for another minute. See, just give it one more minute here and see if we have any other questions come in. While we are waiting, just a couple of bookkeeping things to let everyone know. So this session will be over shortly, and I just wanted to remind you, you can switch to the next session in Whova, and that's going to be titled JMAG in Research and Development. And so feel free to do that. That'll start soon. And just as a reminder, if you run into any kind of technical issues, try refreshing your screen. So that should help. So let's see if we've got any other questions coming in. No, not seeing any. Okay. Okay, well, listen, you can still post those, but I think with that, we'll close this session. And I just wanted to, again, thank Simon and Zach. Thanks so much for your time. And we'll close this out, and we'll let everyone proceed to the next Whova session. So thanks, everyone.
Thanks.
Thank you.
Thank you so much. Bye, guys.
Bye.